and we showed that if whenever there is an changing current fed into a magnetic circuit, due to that the magnetism is developed, and now with uh, simultaneous uh, change of direction of current, the loss takes place inside the uh, magnetic circuit. There is some power loss taking place, and we derived it. So this loss is actually known as the hysteresis loss, and we derived it in the previous class, which is given by kh vf b max to the power n, where kh is a constant that depends on the material of the core, the material, the core material, and it also depends upon the range of the flux density. Now, F is the frequency of the alternating magnetization in hertz. V is the volume of the magnetic core in meter cube. Okay, so if it is per unit volume, you can find out the expression. So this value of the loss is depending upon V, the volume, the frequency, and also the B max, and B max raised to the power n, where this n is known as, it goes by the name of Steinmetz, because he first proposed this relationship of the loss, because as we saw yesterday in the previous class, that it is basically the area inside the hysteresis loop, which is a very irregular shape, and just calculating the exact area may be difficult. Okay, so Steinmetz proposed this empirical formula which works. Okay, so this n is dependent upon, is known as the Steinmetz constant, and its value is varying from 1.5 to 2. So given a particular material, the value of n will be given. So that is the hysteresis loss expression, which we discussed in detail in the previous class, and which happens when a piece of iron is simultaneously magnetized and demagnetized, or magnetized in the opposite direction, and so on. Okay, so the entire phenomenon we saw in the previous class. So today we will discuss another loss that takes place inside the any iron piece which is magnetized, which is known as the eddy current losses. So the ferromagnetic material of the core is subjected to time varying flux. It induces EMF in the core, which in turn produces circulating current in the core. Now, these eddy current losses, we will at the end of this discussion we will end up with a formula. Okay, so but we are not going to discuss the formula in this class. So there is an elaborate derivation of the eddy current loss formula also, which we are not going to do in this class. I will just directly write down the expression. Okay, if
Sir,
anyone,
excuse me, sir. Sir, can you present the PPT, because currently the font is very small. It's tough to read.
is it? I'm presenting.
Yes, sir. Yes, sir.
No, sir, you are presenting the screen, but I'm talking about the PPT.
The full screen.
So go to the land views of the portal.
Can you see now?
Yes, sir.
Yes, sir.
Yes, sir, it's better.
Okay, I thought it was in the presentation mode. Anyway, so today we will discuss about another loss that takes place in whenever there is an alternating current passes through a coil, and the core is basically some ferromagnetic material, which is known as the eddy current loss. Now, in this class, we will not going to discuss the derivation of the eddy current loss. It is available in the books. Because it is a detailed discussion. Because of the shortage of the time in this semester, I cannot do the derivation, but it is available in the books. I will give the reference. Any one of you are interested, you can follow that reference, that derivation, how the formula comes is shown there. But as a student, I also have learned this loss formula, but in this course, because of the shortage of time, I cannot discuss. So what actually happens is, whenever there is a changing flux, due to the time varying EMF, it produces circulating current in the core. That means in the piece of iron. So these currents generated are called eddy currents. Okay, so the effect of eddy current is to dissipate energy in the form of heat. So as soon as there is current, whenever a current flows through some element, there is loss. Okay, so if there is some current flowing through the ferromagnetic material, there will obviously be some loss, which will actually dissipate in the form of heat. So if the magnetic material is made of solid iron, the power loss in the core would be considerable owing to very low resistance in the core. So if it is a ferromagnetic material, there will be power loss inside the core. Okay, this iron will get heated up. Okay, and ultimately this heat has to be evacuated. Otherwise, the equipment will get heated. Okay, so if you see any equipment, if you see your home ceiling fan or table fan, after it is run, if you touch the body, you will find that it is hotter than before it was started. Okay, so any electrical equipment gets heated up when it is used, and the heat generated here is in the iron piece, in the ferromagnetic material. Whenever there is a current is passed through the coil that is around it. Okay, so one loss we discussed in the previous class, which was the hysteresis loss, which is due to simultaneously changing direction of the current. Okay, because of the alternating nature of the current, the flux lines will also change, and that gives rise to the hysteresis loss. And we saw the hysteresis characteristics, and the hysteresis loss, we actually showed that it is proportional to the area under the curve, the area enclosed by the curve. Okay, so what type of ferromagnetic material is desired? Can anybody tell? To minimize hysteresis loss?
So which has low area.
Yeah, so if
The
you have
area of the hysteresis curve has to be low, very small.
low, so we saw that the hysteresis loss is proportional to the area under the curve, inside the curve. So if you have some material whose area is very low, or ideally if it can be zero also, then that is the best material because it does not have any hysteresis loss. So that was hysteresis loss. But eddy current loss is another loss which, because of this alternating nature of the flux, a current itself, a circulating current gets produced inside the piece of iron. And as soon as there is a current, there will be the I square R loss. Current flowing through some resistance will generate an I square R loss. And so this piece of ferromagnetic material will get heated. Okay, so if you have a piece of material like this, piece of iron, and there are the flux lines. So what actually happens is, due to the flux, there will be a circulating current generated inside the piece of iron. Okay, and because of this, there will be the heat loss. So the material will get eventually heated. So as I just told, that if you touch any electrical equipment, okay, your home ceiling fan, or ceiling fan is very high, but if you have a pedestal fan, if you touch the body of the fan after switching it off, you find that it has become hot. Okay, so if you touch your the refrigerator when it is running, you will find that it is hot compared to when before it was running. So what is the solution to this? There is a current. So the solution is how to minimize this current. Okay, so the current can only be minimized, if you reduce the cross-sectional area. So the current is flowing. So if it faces a smaller cross-sectional area, then there will be, so rho L by A. If your A is less, then your resistance is less. Resistance is high. So
I have a doubt in the diagram. So the flux is coming parallel to the phase where the eddy current is being generated. Shouldn't the eddy current plane be perpendicular to the flux?
No, this is some arbitrary direction I have shown. Okay, so when all the details could have been discussed if I did the whole derivation. Okay, if I did the whole derivation of that, of the this thing, yeah, that is correct. So all those rules of this will be there. The generation of the current, that Fleming's right hand rule, everything is valid. It follows that only. There cannot be a current generation without that rule. Is it clear?
Yes, sir. Okay.
I have shown the So one way to reduce this effect of this current is if you can increase the resistance. So here in the diagram, as it is shown that it is a piece of solid ferromagnetic material. The resistance can be increased, if this solid piece is made of, made of some fine sheets and all kept together. Okay, so if you have a piece like this, instead of a single solid material, if you if you have laminations, it is in electrical engineering language, this is called lamination. If you have laminated sheets available and then keep them together and make the structure, then what will happen is, and these laminations are again, they are insulated from each other. Okay, they will not be touching each other, so they will be insulated from each other. So in that case, they don't find a path, and ultimately the area is reduced. That will lead to increase in resistance, and that will offer uh, mm, resistance to the eddy current path. Okay, this is how the eddy current losses are. Eddy currents can be reduced by making the core, the ferromagnetic material, made up of laminations. Okay, so this is the phenomenon. Okay, that if there is a current carrying, if there is a flux changing, then eddy currents are generated inside the um, ferromagnetic material, and this eddy current will lead to I square R loss, and if there is I square R loss, there will be heat generation, and that and it is entirely wastage. Okay, so, and it will, if your equipment gets heated, it can have other problems. Okay, so then the heat has to be released. So one way is to reduce the eddy current loss, and that is achieved by making the ferromagnetic material in the form of lamination. The laminations, so this core is made of laminations that are insulated from each other. So the resistance of the path is increased due to the decrease in the cross-sectional area, and the flow of currents being confined to the respective laminations reduces eddy current loss. Okay, so this is the eddy current phenomenon, which will invariably happen in the when the source is AC. Now this eddy current has also one advantage. All of you must have seen and traveled by locomotives, electric locomotives and all. So there, that huge train has to be stopped whenever it goes from one destination to another. It has to, suppose the train comes from Howrah to Kharagpur. At Kharagpur, it has to stop. Okay, sooner or later, you people will be started coming here. Okay, you have to travel by train. So the best way to come to Kharagpur is by train. So the one thing that is there in the electric engines is to brake the train, is to stop the train. The braking has to take place. Like all of you must have, must ride bicycles. Another thing that you will be requiring in the campus. So all of you should learn bicycle. So in the bicycle, one thing is the brake to stop the train, to stop the bicycle. So in the train, there is, in the engine, there is one braking arrangement which is called eddy current braking. Okay, that is again an advantage of the eddy current. The eddy currents are used to brake the system. Okay, so all those things, you will also be doing, those of you who are in the electrical engineering will do some experiments in your third year that actually makes use of the eddy current braking phenomenon. Okay, so that is one advantage of eddy current. But otherwise, eddy currents are introduced, and it has to be minimized, and that minimization can only be done if the core is laminated. Okay, so you understand the meaning of the solid core as well as laminated core?
Sir, are the plates are connected in parallel connections?
Plates are placed one after another. Okay, the plates are placed one after another. They allow the flux lines, but they must be they are insulated again from each other, so that it does not make a solid core. Because as soon as it makes a solid core, it will increase the area. As soon as it increases the area, it will reduce resistance, and there will be a lot of eddy current and eddy current losses. Okay. I will give the reference at the end. If any one of you are interested in the derivation of this, the reference I will give, and you have to basically go from there. We cannot discuss this derivation in the class now. So an induced EMF, and as the induced EMF as well as currents both are proportional to the frequency, Okay, and the flux density, it is reasonable to expect that the power loss due to eddy currents will be proportional to the square of the frequency and the square of the flux density. So that is the EMF generated as well as current. Since they are both of them are proportional to frequency, the power loss due to eddy current is also proportional to square of the frequency and the square of the flux density. It actually comes out of the derivation which we will omit for this in this class. I've just used this sentence to explain that. So in that case, an empirical formula for the eddy current loss is given by this. P is equal to KE F square B max whole square tau square V, which is in watts. So this is the empirical formula of eddy current loss, which can be derived. Okay, so that derivation, the reference I will give. But in case of the hysteresis loss, it was an empirical formula given by Steinmetz. Okay, so that is known as the Steinmetz formula. But this formula can be exactly derived, but we will omit in this class. So this K is basically called the characteristics constant of the core material. F is the frequency of variation of flux. Okay, so the time varying. So if the current, if the EMF source is having a frequency F, the current will also have a frequency F. The flux will also have a frequency F of variation. And Bmax is the maximum flux density. You already know Bmax. Unit is Weber per meter square. We have done some numericals, and you'll get a lot of numericals using Bmax in the books. Tau is the thickness of the lamination sheet. This tau is basically the thickness of the lamination in meters, and it is it comes out of this derivation. And V is basically the volume of the material in meter cube. So this is the empirical formula for the eddy current loss. And for the numericals, what is important is, if assuming other V and tau constant, it is proportional to F square and B max square. There's a lot of problems are there in the tutorial sheets and in the other books relating to these eddy current losses also.
Sir?
Now,
Sir, here tau is the thickness of each laminated sheet or the total block of lamination?
Just one single laminated sheet.
Okay.
Thickness. Now, as I told that if you are interested in this derivation on the eddy current loss, it is sometimes covered also in the class, but due to shortage of time, we will not cover. Okay, you have to read these books. A very famous book on electrical measurements by Golding and Widiss, and it is available.
Excuse me, sir. Sir,
derivation is important
if we take,
Sir,
if we take many different layers of laminated sheet, and in that, in each layer there are eddy current losses, and then for each of the layers, the losses, when we add up, the total loss won't be the same as that in case of.
That you see, because if you, as soon as you reduce the thickness, the area will, the area will reduce. That will basically result in increase in resistance. Increase in resistance becomes current will reduce. Okay, so it is one is related to the other. So it virtually results in reducing the thickness. Basically, results in reducing the increasing the resistance. Increasing the resistance leads to
Sir, this is the power loss of eddy current power loss for just one laminated sheet. Then we just multiply this by the number of laminated sheets to get the total power loss.
No.
Yes, that is.
This is the power loss due to the whole core. Power loss of the whole core.
The power loss of the whole core.
Yes, when the immediate, because you see that volume V is the volume of the material. Okay, and T is just the tau is basically thickness of one lamination. This is the loss for the total entire volume of the material. V is there in the derivation.
So we don't have to multiply it by the number of sheets to get the total power loss. It's
No.
Okay.
It is for the entire core. Okay, anybody interested?
Derivation.
So derivation is also asked in exam.
It can be asked, but since we are not doing, it will not be asked. Okay, since we are not doing in the class, but if we had some more hours, I could have done it in the class of the derivation. But if any one of you are interested, you go to the reference. chapter 14. Okay.
So is the eddy current loss in each plate is equal?
Eddy current loss in each plate, assuming that they are equal. Because we are not varying the thickness. Okay, so this is the eddy current loss for a uniform solid core, solid laminated core. Okay, if you remember the picture in my earlier slide, instead of such a solid core, we will have such laminated core, and assuming they are uniform, they are of the same thickness. Then that is the formula. Okay.
Yes, sir.
So these two formula you must remember. In hysteresis laws, it was proportional to F, B max to the power N. Okay, and then less part was volume and all those things were there. But here it is F square, B max square. There the power was N, B max to the power N, which is an empirical formula because it is area under the hysteresis loop, which since it is a irregular shape, finding the area itself, maybe you can spend your whole life to find the area of that hysteresis loop. Okay, because the boundaries are basically some complicated shapes. So the Steinmetz gave an empirical formula out of several experiments and gave that empirical relation which works for different material. But this formula can be derived and it is available here. Okay. So, okay.
Yes, sir.
So let us start with the transformer principles. So a transformer, we have already discussed so many times that electric energy is basically generated in the generating station where the resources for electric power generation are available. Okay, so it is basically generated in generating stations. And by resources, what I mean is, if it is a thermal power station, its resources are coal and water. Okay, if it is oil-fired station, the resources are oil and water. Okay, if it is a nuclear power station, water will be required, and then some nuclear fuel. If it is an hydel power plant, it has to be obviously located in the hills and where there is plenty of rainfall. So it is generated from any generating station. Now, this energy has to be transmitted over long distances, where it is utilized in industries, houses, offices, etc. So this we have been mentioning so many times. Like suppose some hydroelectric plant is there somewhere in the Himalayas, maybe Bhutan. Okay, so then that has to be the generated power. Power cannot be saved like other commodities. It has to be used up. Yeah, because its storage is not that efficient. Okay, if you want to store it in some batteries and all, it will not be that efficient. You may need a huge number of batteries to store it. So electric power is such a commodity that it has to be used up, and the only way to do that is it has to be transmitted from the generating stations to the places where they are used up in the big cities through the transmission lines. So and the consumers are basically large industries, small industries, the houses, offices, railways, airports, schools, hospitals. Everybody is a consumer of electrical energy. Now, the power generation voltage is normally at the level of 6.6 kilovolts to 33 kilovolts. That is the generator output voltage. I have shown the diagram initially in my module A lectures. That is the generator output voltage is from 6.6 kilovolt to 33 kilovolts. And it is uneconomical to transmit large amounts of power over long distances at this voltage level. So at the generation voltage level, if we transmit the power, it can be actually be mathematically shown that it is not economical to transmit the power at the voltage at which it is generated. Because as the power is transmitted over long distances through long transmission lines, maybe several hundreds and thousands of kilometers long, there will be large voltage drop. there will be large voltage drop in the lines. Okay, some power generated at Jharkhand, and if it is transmitted to Bombay, okay, Mumbai, it will, the distance may be more than 1,000 kilometers long, maybe 1,400 kilometers long. So there will be, over this long distance, these long transmission lines, they will also have, the resistance, reactance and all. So there will be voltage drop throughout these lines. And so by the time it reaches Mumbai, there will be a huge voltage drop.
Sir, why
Then
there
there
is a
will,
voltage drop?
huh?
Why there is a voltage drop?
You have to tell why there is a voltage drop. Why do
So the
voltage drop
transmission
happens?
lines also have some impedance.
Is it clear? Who asked this question? But anyway, is it clear? Whoever asked the question. The voltage drop.
Yeah.
So if you have real resistance, the more and more you have impedance, there will be more drop. Okay, and if your distance is more, then your impedance values will also be more. The wire will have some resistance, the wire will have some reactance, and it will increase because it will be directly proportional to the length. Rho L by A, R is equal to rho L by, if you just simply consider resistance, it is directly proportional to the length. So if the resistance increases, there will be voltage drop, and more the resistance, the voltage drop will be higher. And more the value of resistance, there will be excessive losses also. In the line, in the transmission line, that is, you must have seen the transmission line when you travel by trains or buses. There will be heat generation because there is current and there is resistance and it is dissipated to the atmosphere. And that heat is basically useless. Okay, the power generated Jharkhand before it reaches Mumbai, it has wasted a lot of the power in the form of heat, in the form of voltage drop. But if you are a resident of Mumbai, you will not be willing to pay for all the losses. Okay, you will only pay for the bill which is entering your house, which you are consuming. Okay, for your domestic requirement, for your industry or your office, whatever you are consuming, you will pay. So it is uneconomical to transmit large amounts of power at the generation level. That is 6.6 kilovolts, 233 volts. So different generators are there generating power at different levels. So it is basically uneconomical. So the reduction in voltage drops and power losses can be achieved by increasing the transmission voltage. So the voltage at which it is generated in the generating station, if the voltage can be increased and then dispatched, okay, so this reduction in voltage drop and power losses can be made. The voltage drops and power losses can be done. Okay, and this can be mathematically shown. So all this whatever I am telling is basically part of some mathematical derivation which we will not do in this class, but it can be shown that the voltage drops and the power losses reduce if we transmit the voltage at high voltage. So what we actually need is the generator is generating at a certain voltage, 6.6 kilovolt or say 10 kilovolts or 20 kilovolts or 33 kilovolts. That voltage has to be raised to a certain value. So for raising this voltage, in the AC transmission voltage levels in India are basically these levels: 110 kilovolts, 132 kilovolts, 220 kilovolts, or 400 kilovolts. You must have seen in the transmission towers, there will be some symbol of danger, 440 kilovolts, 400 kilovolts, with some, danger sign there. Okay, 220 kilovolts with some danger sign there. So that is because the voltage of the transmission lines, the voltage level of the transmission lines, the voltage level of the wire at the wires in these huge structures is actually at this level, 110 kilovolts. Kilo means 10 to the power 3. Okay, it is 1 lakh 10,000 volts, or if it can be 4 lakh volts. Okay, if it is 400 kilovolts. Okay, so these are basically the levels. So from the generation voltage to this transmission voltage level, there has to be some equipment to do this. Similarly, in our homes, the utilization voltage is at the level of 230 volts or 414 volts. In our homes, it is that we don't consume at high voltage. Why? What is the problem? If it is high voltage, what is the problem? But there is no problem.
So the equipments are powered at low voltage.
Yeah, but what is the problem with high
Safety
voltage?
So
purpose.
if the voltage is high, then the
Safety purpose.
according to the resistance of and impedance of each equipment, the current will also be high, and so it will burn up the appliance or something like that.
Everything is required. If it is high voltage, you will need special requirement to handle that voltage. Okay, if it is some, suppose all of you have handled some circuit in your school level. Okay, some small battery circuit. If you directly touch that wire, also nothing will happen, even if it is on. But at this voltage, you will get a shock, and at kilovolts, it will be danger. Okay, so at higher voltages, you will require special protection systems, and if there is protection, the cost will also rise. So the utilization voltage of the domestic and commercial industrial users are basically 230 volts, 450 volts at this level. Similarly, there are in the industry there are motors these are actually some of the standard voltage levels. There are industrial motors that operate at 3.3 kilovolts, 6.6 kilovolts, 11 kilovolts. Okay, our domestic motor. All of you must have seen the domestic motor. In our house, there is some motor to pump the water from the ground level to the top floor level, or there is some motor inside, or the fans inside the refrigerator everywhere. But in the industry, the motors operate at 3.3 kilovolt, 6.6 kilovolt, 11 kilovolt. Okay, if you go to some industry, steel plant, a power plant, if you even visit some, in every city there is a water pumping system. Okay, so you go to the city of Calcutta, there will be several water pumping stations located on the bank of the river, and they supply power to the whole of the city. So
Yes,
there
I went to the Srirampur water treatment plant recently for the EVS project. I saw the power supply and the motors there. They were big.
Big motors. What was the rating of the motor? Do you remember?
The exact electrical ratings I had not noted down because that was not part of my project. But I saw the motors. They were very big in size, like taking the place of an entire room, like
Yeah.
that.
Were they horizontal or vertical?
So
But anyway,
the
next time you see this, you should watch this. Okay, so
yes,
there basically you will find motors where Soham had gone. So water pumping stations, which is supplying
Tanmay,
what? Oh,
Tanmay,
Tanmay. Okay, Tanmay. Okay, the voice looks similar. Okay, Tanmay. So wherever okay, it is part of your EVS course. What was it?
environmental protection problems and solutions to provided by your area.
Okay, so that is having some credit.
Yes, I think so.
Yeah. Anyway, so I think all of you are. I am not aware of all these courses, but but I know that people have to do these things. So if all of you have to go visit different locations, you go and see. As Tanmay has told that he has visited the water pumping station in Srirampur, which will actually supply water to the whole city. Or there may be several such pumping stations. Just one pumping station will not do, and that is also not good for the redundancy. If some problem develops in that pumping station, the water supply will stop. So they will have multiple stations. So there, in the river pumping stations, the motors are huge. As Tanmay told, it is in the form of in the diameter, maybe in the form of like the room only, and the motors will be rated in megawatts. It is not even in kilowatts. It will be in the range. Big motors will be there in the range of megawatts. So those motors actually, so Tanmay and others, whenever you visit next time for whatever EVS courses, since you are doing this electrical course, you should also read the nameplate of the motor. There is everywhere there is a nameplate. Just like your house has a address, your name, some address written outside every house, house number, locality, all those things. So for motor also it will be written. And if it is allowed, you just take a snapshot. That will help you to understand what the rating about that motor. But obviously, you have to take a permission of the authorities whether they allow it or not. Okay, so these motors are actually operate in kilovolts. Their input voltage is in kilovolts, 3.3, 6.6, 11 kilovolts. So at the generating stations, this voltage has to be stepped up to the transmission voltage level. Okay, these diagrams I had showed earlier, when we discussed about the general power system. So this voltage, the generation voltage which is at 6.6 kV or say 10 kV or 15 kV, the voltage has to be stepped up. The voltage has to be stepped up to the transmission voltage level, which is 110 kV, 132 kV, and so on. And then at the customer level, at the consumer end, the transmission voltage has to be stepped down also, so as to be suitable for utilization. Okay, so if it is a domestic customer, a domestic consumer, then the voltage has to be stepped down to the level of 230 volts, 415 volts. If it is some industrial customer, the voltage has to be brought down to 3.3 kilovolts and so on. So for this stepping up and stepping down, okay, so in the entire power system, there are many places where the voltages have to be stepped down and sometimes voltage have to be stepped up. Okay, what we actually need is basically the transformer. Because at the transmission, when the power has to be transmitted at the generating station, what you need a step up transformer, because the voltage has to be raised to the transmission tower level. And when that power has reached the city, where say Mumbai, Delhi, or Ranchi or some city where there are a lot of consumers, so what has to be done is the transmission voltage has to be stepped down so that the consumers can use it. It can be domestic consumers who can use it. It can be some industrial consumers who can use it. And so for doing this stepping up and stepping down, what you basically need is the transformer, and which is a must in every any electrical system, any AC based electrical system. Okay, so for this reason it has to be studied in details in this course. So what is a transformer? It is basically an electromagnetic device that is used to transfer energy between two or more electrical systems with the magnetic field as the coupling device. The coupling device is basically the magnetic field. So electrical energy is transferred to the magnetic energy, and that magnetic energy is again transferred to the electrical energy. So in between basically comes the magnetic field. So it is basically an electromagnetic device used to transfer the energy between two or more electrical systems. As I told, it can be used to step up or step down the voltage levels.
Sir, why is it said two or more? We can only do two, right? Primary and secondary coils.
No, there can be more also. There may be, but those things again, I am not going to discuss in this course. There can be two. There can be two. There can be two secondaries. Okay.
So maybe there will be like one rectangular core will be there, and along with that, an 8-shaped something like that, and we can have more than 2 coils there.
Yeah, this is Soham or Tanmay who is. Huh?
So both.
Both, okay. So no, see, those are the shapes that you are mentioning is taught at the school level. Okay, here also we will mention the space, but more and more complicated shapes are also there, depending upon the application. Okay, there may be say two secondaries. One secondary will develop at one voltage, the other secondary will be at another voltage. Okay, there can be three-phase transformers. Right now, in this course we will only discuss single-phase transformer. There can be three-phase transformer, just like you have studied the three-phase system. There can be three-phase transformer. Okay, so like there will be RYB in the primary, RYB in the secondary. So that is not necessarily just two coils. There are more coils. Okay, Soham and Tanmay and others.
Yes, sir.
So it is basically transfer of energy between two or more electrical systems. Okay, so from somewhere the electrical energy will be given, and there will be somewhere electrical energy will be passed. But the main thing is there will be either step up or step down of the voltage levels. So a transformer thus is an important and essential component of an electrical energy system. You cannot have an electrical energy system with transformers. And all of you must have seen transformers. You know, if it is as you walk down the street, you will find some transformer mounted on the roadside. Okay, if you come to see the Durga Puja in Kolkata, you will find that during the puja, the power company will put up extra transformers in the localities because the power capacity will be more. So all of you should watch out. If you have not yet seen, you should watch out for transformers whenever you visit, walk down or go out of your house. You must, in either side of the road, somewhere you will see some transformers. But obviously, these transformers are distribution transformers. They are taking power from the grid and distributing in our locality. But then similarly, there will be generator transformers in the power stations. So a transformer is an important and essential component of an electric energy system as it makes it possible to generate electric energy at the most economic level, transmit the electric energy at the most economic transmission level, and distribute the electric power at the voltage suitable for electric drives, lighting loads at your homes, the heaters at the consumer end. At the consumer can be anything. It can be some motor, the electric drives, the whole railway locomotives, lighting loads, the street lights. It can be the heaters at your home. Anything any application you think of needs electricity these days, and it is coming through some transformer somewhere. So in a common form, the transformer basically consists of two coils mutually coupled through a ferromagnetic core. There are two coils mutually coupled through a ferromagnetic core. So there is a single ferromagnetic core and the coils are coupled through the ferromagnetic core. Okay, the coils are not physically in touch. Okay, so the one coil will generate the flux. It will pass through the ferromagnetic material and it will go through the coil of go through the second coil, and that is how a transformer is by construction. So the ferromagnetic material basically ensures that high value of the magnetic flux between the coils. That is the property of the ferromagnetic material, that to allow high values of the flux. If it is so, that is how the ferromagnetic materials are used as a magnetic material. So we have discussed what is the ferromagnetic material: iron, nickel. Okay, there are many alloys that make good ferromagnetic material. And since the core is mostly iron or its alloys, the transformers are called iron core transformers. So most of the transformers are basically iron core transformers. So one of the coils called the primary winding is connected to the power supply to receive power. The other coil called the secondary winding is connected to the load circuit and delivers power to it. Okay, you must have done in your virtual lab, maybe there is one transformer experiment. I don't know you have already done it or not, but
Yes,
anyway,
open circuit test and short circuit test of single phase transformers.
So that is the experiment is there, and in fact, if you were here, you would have actually handled the transformer. It is a 1 kVA transformer that is there in the lab, but in this mode, only the virtual mode is possible. But I wish all of you, when you come back here, the thing is you visit the lab and see the setups by yourself, which you are doing virtually. And actually, in that virtual lab, we have tried to make those software very much as close to the setups as possible. Okay, so you should see those setups also. Okay. So this is some general description on the transformers. Okay, so gradually we will be going to the transformer principles in details, the construction, how they look like, and then we will see what else can be done. So the response of magnetic circuits to AC voltages. So this is the topic that we will discuss now. So this is basically the transformer core. Okay, so though I have shown a one side view, but these are all, this is having a cross section, okay, a square cross section, or it can be some other cross sectional view. So what actually happened is, so this is basically called the core of the transformer over which we put up the windings. So we put up the windings on the core. We put up the windings of the core, and so this is how we put the windings on the core. So as soon as you put the windings, obviously you can count the number of turns, which is actually going to matter now. Okay, and suppose there are n turns. So over a piece of ferromagnetic material, which for the time being we have assumed in this shape of a rectangular shape. Okay, there can be other shapes also, we will show later. Okay, the simple thing is, so this is the ferromagnetic material, that is the magnetic material that is going to act as the coupling device. If you remember, we use the word electromagnetic coupling. So this ferromagnetic material is going to act as the coupling device. Why? Because in one of the arms of the ferromagnetic material, what we have done is the coiling. Okay, so we have the coiling in a particular way, and as we have coiled it, okay, we give it some name. Okay, so between A and B is basically the coil, and what we can do is we can supply a voltage to this coil, and depending upon the direction of the voltage, obviously there will be a current. There will be a current which is known as the, say, I phi. Some current is flowing. I phi, why have I used the notation phi as a subscript? Because this current will actually produce a flux in the magnetic path. Okay, so this current will actually produce a flux in the magnetic path, and you know how to find out the direction of the flux. For the current going in, by what rule do you find the flux direction?
Right hand thumb rule.
Right and thumb rule.
Right hand thumb rule. That means you hold the wire in the direction of the current with the thumb pointing in the direction of the current. Okay, so you hold the wire in the direction of the current with the thumb pointing, then the other fingers basically shows the direction of the flux. So it is clear now from the diagram why this flux direction.
Yes, sir.
Yeah. So now, so what will actually happen is, here this end, from this end the current is entering. So obviously this end is at a more potential than the lower end. That is, the end A is at a higher potential than end B. So if you do V minus C is basically equal to 0 magnitudinally, and so your EAB, that is the potential between A and B, is nothing but the L d I phi dt. Okay, so that is basically the voltage magnitude that is generated. Now, where L is basically the inductance of the coil, and we know what is the L, what is its unit. Okay, we have done a lot of numericals using L for AC circuits. Okay, so gradually we'll go to those things. So L offers, what do the L effect offer in the circuit? L, it offers basically reactance. Whenever there is an AC, due to L, there is a reactive effect into the circuit. So V is equal to E equal to L d I phi dt, and which is equal to EAB. Now, since this applied voltage is sinusoidal, the applied voltage is sinusoidal, assuming a linear magnetization of the ferromagnetic core. So this assumption is very important. Linear magnetization of the ferromagnetic core. We have seen the ferromagnetic core is, what is having what type of characteristics? The BH curve. It was having an S type of characteristics. Okay, so it starts sharply, and then from the knee region it bends, and then it saturates. Okay, so what we assume right now is the magnetization characteristics as if you are operating only in the linear zone of the magnetization characteristic. So if the voltage is sinusoidal, so then the current, magnetizing current, is also sinusoidal, and it is represented by, say, I phi is equal to, small I phi is equal to root 2 capital I phi sine omega t. Okay, so if your voltage is sinusoidal, then your current is also a sinusoidal. Why is this root 2? Why this root 2?
RMS.
So because here
RMS.
So here we have assumed this capital I phi is the RMS. So the maximum value is basically root 2 I phi. Okay. So I phi is the RMS value of the magnetization current, and omega is the angular frequency given as 2 pi f radians per second. Angular frequency given as 2 pi f radians per second. So your V which is equal to E, if you just substitute here, you get root 2 omega L I phi. Root 2 omega L I phi sine becomes cos. This omega is coming because of the differentiation. So this is basically the effect of V. So represented as a sine, it is root 2 omega L I phi sine of omega t plus pi by 2. Is it okay? Cos to sine?
Yes, sir.
Yes.
Omega t
Yes,
plus omega t plus pi by 2 is in the second quadrant. Sine is positive, so it is positive. And there is an odd multiple of pi by 2, so sine becomes cos.
okay, sir.
Okay, so sine becomes cos. So these two expressions are equivalent. So why are we doing all this? Because ultimately we want to convert it to the same trigonometrical quantity. Because ultimately what we will do? What we will do?
Phasors.
We will find phase difference.
We will do for phasors. Okay. Because this is AC, so everywhere we have phasors. So your I phi, if it is I phi is equal to root 2 capital I phi sine omega t, your V is equal to root 2 omega L I phi sine omega t plus pi by 2. So what is the relation? The voltage is
Leads.
leading I phi as well as phi. Okay, suppose we assume that I phi and phi are along the same. Okay, so the voltage is leading the magnetizing current. I phi is the magnetizing current as well as the magnetizing flux by an angle pi by 2. So just this is some manipulation that we substitute omega L I phi as capital E. This becomes equals to root 2 E sine omega t plus pi by 2. So E is equal to omega L I phi, the RMS value of the inductance reactance drop. Omega L I phi, if you remember the term omega L, it is basically the
Reactance.
inductive reactance. Omega L, J omega L, you saw that earlier. So omega L is basically the reactance value due to the inductance. So omega L I phi is basically the RMS value of the inductance reactance drop. And so root 2 E is basically EM, the maximum value of the EMF. EM sine omega t plus pi by 2. Hello. I'm to class actually. Okay, so this is the expression for V. V is equal to EM sine omega t plus pi by 2. So EM is equal to root 2E. So this is all obvious. Whatever the terminology I used, EM equal to root 2E, the maximum value of the induced flux. So if you draw the phasor diagram, which is all of you know how to draw the phasor diagram, and if your I phi is kept along the reference, okay, the magnetizing flux, and obviously the flux is also along the reference, then your E is equal to EAB, which is equal to I omega L, I phi omega L, which is 90 degree ahead. Okay, so the EAB is 90 degree ahead of the magnetizing current or the magnetizing flux. So why are we introducing the flux also in the phasor diagram? Because it is also time varying. As your current is also time varying, so, and we have assumed a sinusoidally varying, so your flux is also a time varying quantity, and since we consider only the linear portion of the magnetization characteristics, it follows the same sinusoidal nature. Okay. Okay.
Yes, sir.
Yes, sir.
One or two sometimes respond. Okay. Otherwise, it appears to me as if it got disconnected. Okay, but not. Anyway.
Sir, I don't get that how that root 2 came.
Huh?
The root 2, how root 2 came in that expression in previous slide.
What is the for a sinusoidal quantity? What is the relation between RMS and maximum value?
RMS equal to maximum by root 2.
So now you understand why that came.
Yes, sir, understood.
So, in the voltage expression, shouldn't it be I phi omega L J or I phi omega L angle 90 degree?
Which one?
So the voltage phasor, shouldn't it be I phi omega L times J?
No, that is basically the magnitude, what it is showing.
Okay, sir.
Okay, but you have to be clear about what is, where it is, because I have rotated it by 90 degrees. So what we have assumed is, just like your current is also sine omega t, your flux is equal to phi m sine omega t. And your EAB is basically equal to n d phi dt. And if you take EBA, okay, just EBA is basically minus E, minus n d phi dt, and you can draw the phasor also in the opposite side. Okay, so EBA is equal to minus E minus n d phi dt is equal to minus n ddt of sine phi m sine omega t is equal to minus n omega, just if you keep on doing the differentiation, cos omega t, or Em sine omega t minus pi by 2. So EBA naturally comes to be lagging EBA. You just see EBA and EAB. EBA naturally comes to be lagging the flux by pi by 2. EBA comes to be lagging the flux by minus pi by 2. Again, EM and all this, these are basically the substitutions. So the RMS value of the induced voltage, what is the RMS value? Will be, what will be the RMS value? Will be maximum value divided by the root 2. So the RMS value of the induced voltage is basically equal to EM by root 2. Clear?
Yes, sir.
Yes, sir.
Yes, sir.
And so if you just substitute EM equal to 2 pi f n phi m by root 2, so you will basically come up with this number 4.44. So 2 pi by root 2, all of you can work out, actually comes out to be 4.44. This is a very mostly occurring number you will now encounter, that the voltage induced is equal to 4.44 f n phi m. Anybody has checked to the calculator? This number is coming?
Yes, sir. It
Yes,
is
sir.
coming to be 4.442.
Yes, sir.
Yeah, so the RMS value of the induced voltage is 4.44 f n phi m volts. So this formula we'll see it will be coming again and again now. So what we have just seen is if there is a electromagnetically coupled circuit and there is a sinusoidally varying flux, it basically induces an EMF. We got that EMF expression, so that the EMF is basically leading the flux or the magnetizing current by 90 degree. And we also got the RMS value of the induced voltage as 4.44 Fn phi m. Phi m is basically the maximum value of the flux. So if it is given the maximum value of the flux density, that is Bm, so Bm into the cross-sectional area will give you phi m, and multiplied by f, the frequency, and n is the number of turns, you get the RMS value of the induced voltage. So RMS value of the induced voltage E is equal to 4.44 f n phi m volts. Okay. Clear?
Yes.
Yes, sir.
So the next thing that we will do today is, we will discuss some amount of about the construction of the transformer. Now, if your A is basically A meter square is the area of cross section of the core, I already told. L is the mean length of the flux path. I already showed the flux path in that rectangular rectangular shaped core. If L meters is the mean length of the flux path, and Bm, that is Weber per meter square, is the maximum flux density of the core, then your E is equal to 4.44 Fn, that phi m is replaced by Bm cross A. So E, the induced voltage, the RMS value of the induced voltage E is equal to 4.44 Fn Bm cross A. Okay. So you see this expression, all of you, if you concentrate on this expression, 4.44 is a constant. F, supply frequency, that is constant. A, cross-sectional area, the size of the core is constant. Cross-sectional area is constant. We are not going to play with the core size. We have taken a particular core so that area A becomes constant. Now, the maximum flux density, Bm, okay, so we decide on the value of Bm. So you see the value of E only depends on what? Value of E only depends on?
So area and number of turns.
So BM.
Why Bm? I'm telling that
N,
Bm is constant.
Number of turns.
N number of turns.
Area also, it is a piece of iron on which we are not, once you have purchased a piece of iron from the market, you are not going to, you have no control over it. What you have control over it is N, the number of turns. Okay, so you see the value of E will basically increase with the number of turns. Sorry, not the, I shouldn't use the word increase. It will always, it will change with the number of turns. It may increase, it may decrease with the number of turns. Okay. So there is another term which is very common in electrical engineering, which is called EMF per turn. So this was the RMF value of the EMF, which is which varies with the number of turns. But if you consider the EMF per turn, then what is it? Which is denoted by ET. Then what is it?
Sir, N को हटा देंगे तो
N को हटा देंगे, so it will be 4.44 F BMA.
B into A.
So that is a very important thing. You know, sometimes those of you who will be studying electrical engineering, so then there is a subject in whether it is taught or not. But if you go to an electrical engineering industry, or if you become a designer of an electrical systems, this is going to come again and again, EMF per turn. Okay, so it is basically constant. So you may have to do with a transformer design with a particular EMF per turn. Okay, so in that case, you have to basically decide the value of BM and A, and then start the design of the transformer. Somebody has designed the transformer also, no? It has not fallen from the sky or somewhere. So this EMF per turn is very important. So EMF per turn will be decided by the value of BM and A, assuming F to be constant. Okay, 4.44 anyway constant. So EMF per turn value will be decided by the value of BM. Okay, at what flux density you are going to use the transformer. Okay?
Yes, sir.
Yes, sir.
Okay, so this ET or EMF per turn is a very important for transformer designs. So this is nothing but 4.44 F phi m. So this BM into A is basically the phi m. So since the current produces the flux, the current and the flux may be considered to be in phase. This we already showed in the phasor diagram. As this current produces the flux, the current and the flux may be considered in phase. And we saw that this voltage is leading the magnetizing current as well as the flux by 90 degrees. Okay, so in the transformer, since there is a magnetizing current in the core, there are a lot of core, means that is the piece of iron core. There are a lot of losses that take place. What are the losses? What are the losses?
The hysteresis loss, eddy current loss.
These are the two losses. So since the core of the transformer is subjected to cyclic flux density variations due to the sinusoidal current, the current that is the alternating source is connected, so it will generate an alternating current which will be sinusoidal in nature. So what will actually happen is the flux variation will also take place in a cyclic manner. So this cyclic flux density variation gives rise to losses which appear in the form of heat. And we have also discussed these losses. So these losses are known as core losses or iron losses. You see, all these losses that are taking place in the form of heat are basically in the iron, in the core piece. Okay, so these are called core losses or iron losses. That is the terminology in electrical engineering, core losses or iron losses. It does not involve the losses. So far you must have done several numericals, where there are losses in the wire. If there is a piece of iron, a piece of wire which carries current, you know what is the losses, I square R loss. That is just due to the current in the wire. But here what the losses are, since there is a simultaneous flux density variation, some losses takes place inside the iron core. And we have also discussed in details about those losses. These losses are known as iron losses or core losses. And these are again two types. We already discussed the hysteresis loss and the eddy current loss. Both of them have been discussed in details. The hysteresis loss and the eddy current loss. So in an electromagnetic equipment, transformer is in electromagnetic equipment. What is the meaning of electromagnetic equipment? It involves both electricity and magnetic field. The magnetic field is created by the electrical input, and the magnetic field is created inside an iron core or a ferromagnetic core. So whether it is a transformer or it is an electric motor, it is an electromagnetic equipment, and these core losses actually play a significant role in determining the equipment rating, efficiency, and temperature rise. Whenever there is an electromagnetic equipment, there will be permissible limits for its temperature rise. You cannot keep on, and as soon as the temperature is going to rise, there has to be an arrangement that this temperature has to be evacuated. You cannot keep on, some equipment keeps on heating, and then it will get damaged. So the temperature rise is a factor. So if you consider any equipment, if you consider your car engine, okay, when you drive a car, the engine will get heated. So obviously there is a coolant. That coolant that takes away the heat. Otherwise the engine will become hot. Okay, and it may get damaged. There may be fire also. So there is a requirement of a coolant. Similarly, here in any electromagnetic equipment, there has to be there will be temperature rise. This temperature rise, apart from the I square R loss, there are now we see that there are losses taking place which are known as the core losses that takes place inside the iron, and this will actually determine the equipment efficiency and the rating. Okay, because this loss this loss is the power that you are not going to enjoy. It has to be, it is lost to the atmosphere. Okay, so this loss will actually determine the efficiency of the equipment, because it is nothing can be derived out of this loss. It is released to the atmosphere. So this hysteresis loss we have studied in details, that when a core is energized from an AC source, the magnetizing current varies sinusoidally with time, and hence the magnetizing force H applied to the magnetic field is also alternating. We saw this. This leads to that BH type of characteristics. So the variation of flux density when plotted against the magnetizing force H for one cycle of AC excitation is in the form of a loop called the hysteresis loop. In each cycle of magnetization, the hysteresis loss appears as heat. The larger the loop area, greater is the hysteresis loss. So this thing we have been doing. Okay, so the larger the area, the hysteresis loss, and it is basically given by this type of formula, KH Bm to the power n watts. So these are the description of the formula. We have done it earlier. KH is a constant depending upon the material of the core and the range of flux density. F is the frequency of the alternating magnetization. V is the volume of the magnetic core in meter cube. Bm is the maximum flux density of the core in Weber per meter square. And N is the constant called Steinmetz constant, which value varies between 1.5 to 2. So this hysteresis loss, we don't want to spend much time on it. This expression we have derived. We have not derived, we have explained this phenomenon and introduced this Steinmetz equation for hysteresis loss. So KH V volume, F frequency, Bm to the power n. And we have also seen about the eddy current loss, that if there is a time varying flux in the ferromagnetic core, it induces EMF in it and causes circulating currents in closed path within the body of the ferromagnetic material. These currents are called eddy currents. It gives rise to I square R losses. These losses are called eddy losses. So the losses in the core will depend on the effective resistance and the length of the eddy current paths. Obviously, as I told, the objective is to increase this resistance by laminating the core. Another way of increasing the resistance is to use silicon in the core material. Okay, if you use silicon steel, that is steel which is an alloy of steel containing silicon of 4% containing 4% silicon, it has got high resistance. It is also used as the core material to reduce the eddy current losses. Another way is to use laminated sheets parallel to the direction of the flux. Small thickness are used for the construction of the core. So we will show some, we have already shown it earlier. So this is the expression of the eddy current losses as I told earlier that, and it can be derived also, available in the Golding book, where it is proportional to F square, Bm square, tau square, and the volume of the core. So this is basically the just the repetition of the earlier expression. The eddy current loss, which is given by Pe equal to Ke F square, Bm square, tau square V. Now, what we will do today is basically throw some light on how the transformers are constructed, how they look like. So as we have already told that this is one type of construction which is called the core type of construction. The construction of the transformers is basically core type. That is a single rectangular type piece of iron on which on the two limbs, there are different names to these parts also. So this is called basically the yoke of the transformer. And these vertical pieces are basically called the limb. Okay, the vertical pieces are called the limb, and this is basically the magnetic circuit.
What is the yoke? Is it the entire? What is the yoke?
It is basically the entire iron piece. Okay.
The entire volume or the entire area? Just this one.
No. Not area. Area means inside it is hollow. Inside there is nothing. It is I am talking only of the iron piece. Basically the yoke.
Yes, sir.
And only the vertical pieces are called the limbs, on which you put the windings.
But sir, previously we called it as core, no, sir?
Which one? It is core only.
Yes, sir.
It is iron core. Only the vertical, vertical components are called limbs. They are basically synonymously used. Yeah.
The core and yoke are similar name.
No, core is all together. Yeah, yoke and core are maybe synonymous. Yeah.
I mean, sir, yoke and are scientific names, sir.
Huh? No scientific name. See, it is made up of iron core. Okay, or it is made up of some magnetic material, which is ferromagnetic material. As I told, say silicon steel. Okay, where the vertical pieces are called limbs, the vertical legs, and the entire thing is called the yoke. And the way it is shown, I will show some more slides. Where this type of thing you cannot get as a single piece. Okay, it has to be assembled. Okay, I will show some diagram. You cannot suppose as somebody showed, just 1 minute, as somebody saw the motor in the Srirampur, this one water pumping station. It looks like the diameter, maybe the diameter, the width of the room. So such a big iron piece will not be there. Okay, it is basically assembled in pieces. Tell me. Any question?
It is a one laminated sheet. It is right, sir.
Ideally, it is one laminated sheet. Ideally,
Okay,
it is
sir.
one laminated sheet, but even that laminated sheet, if this laminated sheet is in the size of the one wall, okay, it will be, it is not possible. So in that case, it is made up of several pieces.
So,
Okay.
the magnetic circuit is passing through the entire lamina. then why are we only connecting the secondary coil on the limb? Why can't we connect it on the horizontal portion also? Because there also the magnetic flux is going in the circuit.
No, you can do those things. So no, once basically you have multiple coils, then they have to be physically arranged. Okay. So this is basically shown for explanation purpose. I will show the actual winding
okay,
also.
Sir. Okay,
This
sir.
is shown, how it is actually wound is something different. Even this is also not way. It is not done this way. Okay, I will show in some diagram will be there after 3-4 slides. Okay, so this is the diagram that we will use for derivation, we'll do explanation, mathematics and all. But actual physical construction is different. Okay. So this type of single window structure of the core is known as the core type of transformer. Okay, there is also a structure which is known as the shell type, where it looks like this. The shell type of construction. Okay, the shell type of construction. So here also all those magnetic circuit problems that you have done, calculation of reluctance and all those things will come into the picture. There will be the MMF due to the current, okay, and then generation of flux will get distributed. So parallel paths, parallel reluctance, equivalent reluctance, all those things you can do now. Okay, so this is basically the shell type construction. Again, this is the yoke and the vertical ones are basically the limb, and this is the magnetic circuit. Okay.
Yes, sir.
So this is the how. So we are going to discuss discuss about the construction. So this is the how the iron pieces are constructed. Yeah.
Sir, in the middle limb there are two magnetic circuits.
There are two.
Like the magnetic circuits, there are like two magnetic circuits in the middle limb where the windings are connected.
See, if to one winding some voltage source is connected, it will generate a flux, which will get distributed. Okay, which will get distributed in the two paths, and if the two paths are having the same type of reluctance, they will exactly divide.
So I can't understand how is it getting divided into two pathways in the middle. Like, shouldn't it be in the same pathway because it's all part of the same core only?
And the same path means what? Suppose the middle limb, the flux is say 5. So it will get divided now 5 by 2, 5 by 2. One will go on the left, another will go on the right.
Parallel. We have studied it in previous classes, no? Parallel circuit type.
Yeah, so it is similar to that. If both of them, if it is symmetrical, they will get exactly divided, and then again it will return in the central limb.
No, sir. We are asking about the middle flux line. There are two lines actually. So, like there should be one. Yes, sir. In the middle limb only. The and 5 by 2, 5 by 2. There are two pathways. Yes, sir.
Yeah, 5 by 2. So in the central limb, it is basically adding together is 5.
So then there should be only one line only, right?
Oh, that you can draw. One line is divided. It is just for showing. Yes.
Okay, sir. Got it now.
Okay. So we will discuss some time on the construction, but at least the next few minutes we'll discuss on the construction. So this is how the different possible cores can be. It can be just one single window, or it can be multiple windows. It is called the shell type construction. Now this magnetic core. So as I told, as somebody was asking about this, whether it is a single lamination and all. And as someone of you have visited the water pumping station, you have seen huge machines. So if this single structure is in the form of a wall of a room, okay, that producing such a single piece of steel is also difficult. So the way they are being made is in the form of pieces and then assembled together. Okay. So the magnetic core, there can be different types of sheet steel punching. By using punch sheet steel, this type of core is prepared. So one core can look like this. You understand the structure? Suppose you have one L-type piece and use another L-type, two L-type pieces can be used to make this core. Okay. Instead of a huge
So
rectangular window,
for making such type, we needs the 2L shape, na sir?
the two L shapes.
So how we will join that? So by welding or so by any automator?
Yeah, there all those things, but ultimately it is a mechanical structure. Okay, it has to be mechanically. There will be some arrangement, some hole here, though I have not shown here. Some hole will be there, and that will through which some rod will pass and keep all the sheet steel together. It will not be welding. Welding will be welding will generate less resistance, and then that will cause more eddy current losses. This is just one sheet steel. Okay. Similarly, there can be sheet steel like this. So two E-type structures. Two E-type structures. Okay, you can see one E, two E's, or what do you see here?
So shape 8.
It looks like 8, but it is basically two E-type sheet steels.
So how is the in the horizontal portion, the two horizontal limbs of each ear overlapping? How is it being done?
They will be done.
Maybe
there
there are
are
some slots. One in one
Yes.
there is a hole and other there hole goes in.
Those holes are all there. I have not shown any holes here because ultimately they have to be kept together. But the point of showing these diagrams is that single piece of window that you were seen earlier, the core type and shell type are actually fabricated this way, because you cannot have a big sheet steel of that shape exactly. This type of different small sizes are available, and by assembling them they are actually made. Similarly, there can be a structure like this. What is this?
F.
So it is looking like F shape.
Two Fs. Okay. So this is basically called this. So you can have L-shaped sheet steel. You can have E-shaped sheet steel. You can have your F-shaped sheet steel.
Does the shape influence any of the parameters like reluctance or something like that? Does it influence the efficiency or anything like that?
That is a good question, but that has to be only, once you do transformer design, you'll have to evaluate if there is any difference in their performance. But the point is that structure cannot be made as a single piece. So for that reason, they have to be built using the different pieces. Okay. Now whether they are going to have different performance or not, let us for the time being assume that they have the same performance if their dimensions are the same. If their the cross sectional area and the length, breadth, everything is same. Ideally, they should have the same performance, but they have to be assembled in this way.
Okay, sir.
Okay. So the point is the magnetic cores are built by using this type of different shapes of sheet steel, and in fact some more shapes are also available. There can be a combination of E and I. Okay, E, and this leg is only I. So E and I type structures are also there. I once upon a time designed a transformer where I used EI stampings, EI sheet steel, E and I type. So for different types of, for the different applications, different sizes are available from the manufacturers of sheet steel. So you have to choose which shape you will adopt for your work. Okay. Now, as somebody was asking about the joint, so this is how they are joined actually. There will be some sort of an overlapping to join them. There will be some sort of an overlapping to join them. Okay, so you see that this type of thing will be visible. If you once they are joined, so at the corners they will actually look like this. So these are actually called interleaved joints. So you understand what is the meaning of interleaved joints. If you keep all the sheet steels in one point, in one way, then there will be there may be some biasness towards a particular orientation. So what you do is you do in the opposite way. Okay, interleaved joints.
Yes, sir.
Can you explain again that opposite way orientation?
So
Opposite orientation. See, if you come, suppose you are, you have, like say, okay, when you just another example, simple example I am telling. Suppose you come to, when you come to the hostels here, and then you will, obviously you will have to attend classes and all. Okay, so you have to carry say 10 copies from your hostel to the. Your classes will be in the different departments, Nalanda complex and all. So suppose you all the 10 copies you keep in one orientation. What will happen? Your left side will be thicker. The side you have this, the binding is there.
yes, sir.
Yes,
so
sir.
if you,
Yes.
so if you alternately you keep it the opposite way, what will happen is they will have a uniform thickness, the 10 copies together.
Okay, sir. Now
Okay, so
it's
that is the interleaving has to be done at the corners. Yes, next question.
So while joining in such a manner, there will be some gap in middle, or not, sir?
That gap, they will be, they will be in physical contact, as close as possible. They will be kept tight together. So that air gap has to be.
But sir, at only corner they will be in contact, but sir, at the middle, I think there should be a gap of air.
In the middle, there will be insulation. Between the two sheet steels, there will be insulation. Because we don't want to make it a single piece of iron. Okay.
Okay, sir. Okay, sir.
Because otherwise it will result in eddy current loss.
Yes, sir.
Otherwise we could have made it a single solid piece of
Actually, I'm
iron.
in class right now. Can I just call you an hour later?
Huh? Okay, somebody had a call like me. Okay. Okay, so similarly, in a typical large transformer, okay, power transformer, the cross-sectional view of the core may be like this. The cross-sectional view of the core, that round core, that solid square cross-section that we are telling, it may not be like this, that one limb, the cross-sectional view of the limb may look like this. It will be made up of sheet steels of different sizes. And then ultimately they are bolted. Ultimately, because they have to be kept together. So typically cross-section of a large transformer will look like this. Okay. So that is how they make the circular cross-section. So in actual practice, it will not be the exactly circular piece of iron. Okay. Though in the in your class, some numericals will be there that it is given a circular cross-section or square cross-section and all. But in actual practice, the transformer cross-sections will be somewhat like this because they have to be assembled by keeping sheet steels, and it may not achieve the exact circular cross sections. It may not be exactly possible to fill up these places. because the sheet steels will be available in particular sizes. Okay. Okay.
So this is the side view of
Yes,
the
sir.
transformer, right?
This is the, if you take one limb and if you cut that limb and look from the top, or whether the yoke also, if you cut it and look from the side, just the cross section. Okay, I have used the word cross section there. If you cut the limb and look from the top.
Okay, sir.
Okay, sir.
So similarly, yeah. Similarly, somebody was asking about the windings. So this is how the windings will look like. Okay, so the windings are actually over the limbs, and you see that it is not, though for the sake of explaining in the class we will show one primary, one secondary, but actually the windings are, and one of them will be the low voltage winding and the other will be the high voltage winding, but the windings are actually placed one over the other. Okay, so this is the core and these are basically the windings. Now can somebody tell me which one is the low voltage winding and which one is the high voltage winding?
So red should be high voltage.
Yes, why?
I don't know. I'm like just thinking.
Just because it is
red
red.
in color, I think.
Just because it is red. Yeah.
The red
As
is
it
strong.
is how more areas
Danger.
are red.
Voltage.
Yeah, red is danger, red is high voltage. So as soon as you have high voltage, you need special protection. You need more powerful insulation. So you have to insulate the core from that high voltage winding. So what we do is, to use less insulation, we put the low voltage winding inside. Okay, so that is, so the low voltage winding is the blue one, which is inside, and the high voltage winding is further away from the core, is kept further away from the core. So that is basically the logic. Because as soon as your voltage level rises, you will have to use more and more insulation. So to keep the so to protect the core, high voltage winding is kept on the outside. And in between, so between the core and the low voltage, there will be insulation. In between the low voltage and the high voltage also there will be insulation. Between the core and the low voltage there will be insulation. And between the core and the high voltage also, sorry, the low voltage and the high voltage also, there will be insulation. Okay?
Excuse me, sir.
Hmm.
Sir, I did not understand this, sir, because in previous when you gave the diagram, sir, their left side was input and right side was output, where left side was one voltage and the right side was the other voltage. Sir, but here we have low voltage and high voltage at the same limb. How it is given?
See, that thing that we did was for explanation. Left side, right side, it does not matter. Whether I could have kept in the left and top also, left and bottom also. Somebody was asking. So basically, the same flux lines has to pass through both the coils. Okay, so we can keep even one over the other also. In that case, the flux lines are passing through both the coils. Now, depending upon the voltage level, you will need the different grades of insulation. So for high voltage, you need more superior quality of insulation. So we keep the high voltage coil outside. And they will, in practice, they will actually be in the form of coils, okay, in the form of a spring, in the form of a, if you can imagine a coil in the form of a piece. So basically what will happen is one spring will go inside the other and resemble like this. So the diameter of the low voltage coil will obviously be lesser than the diameter of the high voltage coil. That is, the outer diameter of the low voltage coil will be lesser than the inner diameter of the high voltage coil, so that it will go inside it, and the inside it will be the limb. Is it clear?
Yes, sir. Yes, sir.
Yes, sir.
So this is actually, though that left side, right side, whatever I will show. In fact, I will also show next day, but that is for the derivation understanding point of view. But what I am discussing today is how it physically looks like. Okay, and they will be actually looking like this. So only thing is, all of them cuts the same flux. Now this is another type. If you have the shell type construction, so you see the low voltage, high voltage is alternate. Low voltage, high voltage is alternate, and on the top there is a low voltage, on the bottom also the low voltage. That is just to protect the core from the high voltage. So it is basically attempted when the transformers are designed, that the high voltage be kept as far as away from the core, because if they are kept close to the core, we need better quality of insulation.
So here the high voltage are still close to the core only, like the blue voltage, like the low voltages. They're just alternate to each other.
It is alternate to each other, but you can think of some other improved design also. But at least in the top and the bottom part, they are away.
Yes, and now it's clear.
Okay.
So can you show us a 3D diagram of this?
3D diagram?
Yes, yes. I think that would help.
3D diagram, you can imagine. You can find out from other places. It is just to show a three. So I am not showing the cross section of the limbs. I'm showing from one side basically.
So I'm unable to understand that. So how we are connecting wire of low voltage around that middle part? If we connect, then it will cover all the part, na, sir? So how it is change that?
It is in the form of a spring. Okay, it is in the form of a winding. So if you do one winding in the form of a spring, it will have a diameter. Sorry, it will have an outer diameter. So the inner diameter of the high voltage winding will be more than will be another coil. So the low voltage coil will go inside the high voltage coil.
So the winding is like a helix type?
Yes. So the inner helix diameter will be lower than the outer helix inner diameter. So that is how they are made.
Okay, sir. Okay.
Now, all these transformers, as I told, that they generate lot of heat. In the iron, they produces the core loss in the form of the hysteresis loss and the eddy current loss. So these transformers are actually immersed in a tank. Okay, so you will see on your roadside this type of transformer. This is a small distribution transformer. Okay, they are immersed in a tank, and this tank is actually filled up with oil. This oil actually carries away the heat, and there is a separate arrangement for that oil to get cooled and again returned back to this tank. Okay, now since this is oil, this whole transformer, the iron as well as the coils are basically immersed inside the tank containing oil. So the lot of protection is required so that there is no fire hazard or something, because the oil itself will get heated. So it will circulate, it will leave the heat to the atmosphere and again come back. So this is how a normal transformer will look like. You must all be, must all seen these type of structures beside the roads, and they are usually of this type of color, this ash color or sky blue color you will find. Okay, why this color? because this is the color that that dissipates the heat well. Okay, so this is the color that dissipates the heat well. And then suppose you make it black, then it will itself absorb heat. Okay, so you would not like to make it black. It would like to make it as light as possible. So this is the color that is chosen for transformer design.
So why we can't make it
Blue
white?
light is scattered more in the atmosphere. That's why.
Huh?
Because blue light is the most scattered light in the atmosphere. That's why it reaches.
Yeah, those
best.
will be the reason. It has to actually release the heat. If you can make it white, but can you maintain the white color when you put it in a locality?
Yes.
Will it stay white?
No,
Okay, so
sir, we can't make that white.
So once we have this type of transformer, you will find that it has a support base. There has to be support. There even sometimes you may be finding that there are wheels. It can be moved here and there. And this is basically the tank. And there are special protection systems here. And these are basically the terminals. Okay, so you basically have the low voltage terminals and the high voltage terminals. So these are all the terminals you will find. If you see your locality, you will find the transformers, and you will find that all the wires are getting connected here. And you will see that since you have already studied three-phase, you will find three-phase transformers where the wires of different color will be there, RYB. Okay, the R phase primary will be connected to the R phase secondary. Yellow phase primary will be connected to the yellow phase secondary. So in most of the cases, the distribution transformers will actually be three-phase transformers. So there will be, you will find multiple terminals. You will find 6 terminals like this. And these are all insulators. And then since it also involves oil, there has to be a protection, there has to be a breathing arrangement. This oil is again not exposed to the atmosphere because the oil will get heated. Okay, so there is an arrangement like this through this overhead tank. There is a tank through which there will be breathers. So it is not directly connected to the atmosphere. Through the breathers, there are some, I forgot the name, there are some balls that which can absorb moisture, because you cannot get this oil exposed to the atmosphere or moist atmosphere. So so once this oil gets heated, it basically vaporizes, and there is some safety arrangement which is basically called the Buchholz relay, and it should not rise up to a certain level. If it rises up to a certain level, that means there is chance of explosion and all. So the oil level indicators and all are there, and if such situation is arising, if it will rise up to a certain level, if it is unable to dissipate the heat, then what will actually happen? It will actually stop the transformer. There are protection mechanisms by which the transformer will be stopped. If the heat is not getting dissipated, and the inside the oil is boiling and oil is rising at a certain level, and it is about to spill over. Okay, so there is an arrangement which is called Buchholz relay that is used for protecting the transformer. So in that case, if the oil is not being able to dissipate the heat to the atmosphere, the inside is getting heated, it may even lead to the damage of the transformer. Okay, so to prevent that, they will basically stop the transformer. Okay, the input switches will be all opened so that the power supply is stopped. Then the engineers will look into what is the problem and rectify it. So the protection mechanism is basically this Buchholz relay that is used for protecting the transformer in case the oil is getting heated up and it is unable to pass the heat to the atmosphere. Okay, so that is all about the transformer tank. So all these transformers are, if you should also see in your locality that this type of transformers will be there either at the ground level, or sometimes they are mounted on the poles, pole mounted, which are called pole mounted transformers. And you should also notice these Buchholz relay, these oil level indicators, and these tanks are visible. Okay. So I'm stopping today. So that is more about the transformer construction and why the transformer is required, that we have discussed today. So from the next day, we will do the actual working principle of the transformer along with the numericals and whatever else is possible, topics related to the transformers. Thank you.
Thank you,
Thank you,
sir.
sir.